Hello, good people. Welcome to the first video of the series that is going to involve volumes of solids of revolution. Um, I put together four sections, or rather, Brian has put together four sections, and I agree with this, putting four sections together because the reality is they're all talking about the same thing, except with a slight tweak, right? And we're going to see that tweak here in the examples that we're going to see. But I guess to recap, the last set of videos we were talking about how to find a volume of a solid that's non-traditional. We're not talking about a cube. We're not talking about a cylinder or a cone. We're talking about a solid that's created with known cross sections. And so one of the types, there's two types of problems that the AP exam is going to ask you to create volumes for. One type is a solid with known cross sections. That's what we did before. And that idea said if you know what the shape of the slice is, then if you add an infinite number of those slices, you're going to, within an interval, right, within a window, you're going to get a three-dimensional shape. Now, those slices could be semicircles, they could be triangles, they could be squares. Um, it could be any shape, right? But as long as you know that at any given moment in my three-dimensional figure, if I were to slice it, I see that cross section, then I can use an integral to add an infinite number of those slices put together within a window, within an interval, and create the full volume of the three-dimensional object. So same idea with what we're doing today, but this time we're going to do a solid of revolution. And some people are me, think solids of revolution are a little bit easier because they're very predictable. And as you're going to see here at the end of this video, we're going to create a solid revolution, and you're going to be able to predict what the cross section is most of the time within 10 seconds because it's really a shape that's created by the same process, right? So just like before, we're going to find tiny representations of the volume. In other words, we're going to take slices. We're going to take our three-dimensional shape and imagine us taking slices of it. And when I open it, we're going to see the cross section. And then we're going to add an infinite number of those slices. And by doing that, we're really integrating the expression over the bounds of the region, right? Between my A and B values, my lower and upper limits of integration. So this is the process. It's going to be the same as before. All we need to do is be aware, be careful, and watch out for what is the cross section that we're going to do. However, because we're doing solids of revolution, nice things are going to happen. And so I wanted to show you in this first video, before we get into the details of solving a setup, I want to kind of give you the image of what we're doing. And if I come over here, so I have a three-dimensional coordinate plane, right? So I have an x-axis here in red. I have my y-axis here in green. I have my blue z-axis because now we're in three dimensions, right? So x, y, and z. And what I've done in the x and the y-axis, so the green and the red, which I'm trying to show it to you so that it's kind of flat, that would be the shape that's on your paper, right? X and y-axis. And what we're going to do is we're going to think of this as a shaded region. So I drew, or this GeoGebra animation drew the natural log of x. However, it only drew the natural log of x between x equals 1 and x equals 4. So I'm missing the part that goes down, 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 down towards the y-axis, and I'm missing the part that goes forever increasing towards infinity to the right. But I just get this little part of it, as a matter of fact, from 1 to 4. So what the solid revolution says is if we take a shaded region, and if I were to shade, and I wish I could shade this part right here, the one that's trapped between the natural log of x, the x-axis, and x equals 4. So this little, it's not a triangle, but this little shape right here. If we shade that in, and then we spin it around the x-axis. Now watch, this is exactly what's going to happen. As I spin it around, it's going to create a three-dimensional object. And that three-dimensional object is called a solid revolution. We created this solid by taking a two-dimensional shape and spinning it around an axis, specifically the x-axis. Kind of looks like I don't know, like a topper or like a bullet or something like that, right? But the idea here is I can find the volume of this because if I were to take the slice at any point of this red object and open it, the slice would look like a circle. And it looks like a circle because I'm always doing a solid revolution. And so part of what we're going to talk about is the shaded region, that initial region that I pointed out, is it right up against the axis? Because if it is, I'm going to get a solid, um, I guess a solid of revolution. Like there's no gap, there's no hole. There's just like a full filled up solid revolution, three-dimensional object, right? This is what we're building, but you don't have to draw it, you don't have to imagine it, because the process is predictable, because the cross sections are predictable. This might be a little bit easier than, or almost as easy as, the volumes of solids with known cross sections. Okay. However, before I stop this video, I do want to warn you. Remember, we're tackling 8.9, 8.10, 8.11, 8.12, right? And we're doing four things at once. And the reason we're doing that is because not only are we going to be doing solids of revolution with respect to the x-axis, but we're also going to do solids of revolution with respect to the y-axis. And I'm going to show you one of those right here before we go. And I also want to point out, when you make a slice of this shape, you you do see a circle, but technically it's a disc, right? Because it has some thickness. And so we call this, and what we're going to use, the disc method, because when I take slices, I'm going to get, if I take the slice, I'm going to get discs. When I combine all those discs, then they're all going to add up to a full three-dimensional object. Okay, but let's erase it. So what if I take the same shaded space here, right? Same shaded space, but this time we're going to spin it around the y-axis, and I'm going to try my best. That's not working. I was going to try my best to see if I can align it in a way where you can see it. Again, x-axis in red, y-axis in green, z-axis in blue. The shaded region that I'm talking about is right here. We're going to spin it around the y-axis this time, not around the x-axis. And if I start my revolution, this is what it would look like. Now, as I move this, take a look at the solid of revolution we created. So this is a three-dimensional object. However, there's a gap in the middle. There's a hole in the middle. And the reason there's a hole in the middle is because the shaded region that we had originally didn't butt up against the axis of revolution, right? There was a gap here. So then there's going to be a gap, a hole in the three-dimensional object. So this time, if I were to take a slice, it wouldn't look like a complete circle. It would look like a circle with a hole in the middle. And that's what we call the washer method. So actually, topics 8.11 and 8.12 refer to the washer method as a way to solve volume for the solids of revolution. This is what's happening in the situation, is there's a missing piece in the middle there. Okay, so let's go think about and wrap up this first video. We're going to spin, we're going to revolve a shaded region around an axis. We're either going to get something that looks like this, and we're going to get a disc, or we're going to spin it around and there's going to be space in between, and we're going to get a washer. And in the next video, we're going to talk about how you know when you're going to get one and not the other. If you think about it, this is the circle, right? So this would be pi r squared times dx. Dx would be like the thickness of this disk. If I could draw a thickness, I would draw a thickness. That's not it. But if I could, that's what it would look like. The washer says, well, wait a minute. This is the shaded region, right? But I have to cut out this middle part. And so in reality, there are two radii. There's a big radius from the center to the outer, And then there's a little radius from the center to the inner boundary there, the inner circle. And so then this would be pi big R squared minus pi little r squared dx. And the dx could change if I'm doing it with respect to y, and around the y-axis that would be dy. But these are the ideas that we're going to use. That's the nice thing about solids of revolution. There's only two possibilities. Either I have a disk or I have a washer, and these are the formulas to set it up. So when we come back in the next video, we'll see an example of how we can do that.